Okay, welcome guys. Daniel, do you hear me at the back? Okay, great. So welcome to the Crypto PPML workshop on privacy preserving machine learning. And in fact, this is the fifth time we're organizing it, and we're very excited to have Mariana Raykova to talk for the first talk. So Mariana received her PhD from Columbia University, then she did her postdoc at the IBM Research in Watson. You cannot?
Yes.
Please increase a bit the volume. Okay. Then she was a research scientist at SRI. And then she became an assistant professor. Guys? Now? Okay. Okay, then she became an assistant professor at Yale University. And 4 years ago, she joined Google. So Mariana her work received multiple awards because she has great results on secure computation, on zero knowledge, on verifiable computation, obfuscation, and of course, federated learning. And today she's going to tell us about advanced and challenges in secure aggregation. So Mariana, please help me welcome Mariana.
Thanks, Antigone. Can you hear me? The first question? Okay, so we figured out this mic. We figured out all the technical difficulties. These are the challenges of the live operation. So today I'm going to tell you about some recent, maybe some of my recent results on secure aggregation, and also some of the challenges. I mean, I think it's very ambitious to cover the whole work on secure aggregation in this talk. So that's why you will see my bias selection, and then I'll point you to some of the following talks that will tell us a little bit more. Okay, now let's try to figure out the clicker. It was working a moment ago. They need to focus on something else. So we'll have a clicker in a second. Oh, okay. Now it was very fast. Okay, so what is the question that we are trying to solve here? I mean, this is the question that I think is probably the objective of many works, is a setting where we have many user devices that is generating data. That's where usually the source of all data is. And then we have one central party, one server that wants to learn some insights based on the data that's generated at these user devices. And the goal is to do this without centrally collecting this data and bringing it in one place. So this type of question we will be trying to solve with secure aggregation. And in particular, the objective or the setting that secure aggregation addresses is the one where each device or each client has as an input a vector of numbers. And this comes up in many applications. This vector might be just some analytics, and we want to learn at the central server the aggregation of this analytics. Or in the context of federated learning, these vectors become the gradient updates that client devices are computing based on their inputs and based on the model that this central party is trying to learn. So the goal here is to enable the central server to learn only the aggregate of these input vectors that are coming from the individual devices. So what are the kind of properties we are striving for with these secure aggregation protocols? First, we want to address what is the adversarial model, what we want to protect against. So usually we consider this server to be one of our adversaries. If it wasn't, we wouldn't need these protocols at all. And we also assume that the server can corrupt or impersonate a certain fraction of the user devices. So we want to be able to protect against an adversary that controls the server and also controls a fraction of the user devices. Again, as usual, we want to be able to address either the semi-honest or the malicious setting, where this adversary is just observing the data and trying to learn more, or is trying to actually deviate from the protocol and cause some additional leakage. Also, we want to protect against the clients as well, against clients that might be malicious. And the type of misbehavior that we are trying to protect against when we talk about the clients is about them trying to kind of render the output model useless. And this will be addressed with some of the discussions that I will tell you about input validation, but right, collecting these metrics or these aggregate models is only useful if they reflect more or less the real inputs of the client. So if we have a client that, a single client or a couple of clients that are able to render these aggregate analytics useless, this would not be a desirable outcome. So this is the kind of adversarial behavior we want to address against the client. So here we are talking only about clients that are not necessarily colluding with the server. So, and one additional kind of property, which is required because of the nature of these protocols and the nature of the small client participants, is related to when we are designing interactive protocols. If we're in the setting where we have interactive protocols, we want to account for the fact that these devices are very unreliable. They can drop off at any point, and we want our protocol to kind of finish and obtain output. If our protocol aborts every time there is a device that stops responding, this would not be a useful protocol, because in reality, a certain fraction of these devices will drop off during the execution. All right, and one additional property usually that we want to achieve when we talk about secure aggregation protocols, and especially in the setting when we think that the server can impersonate many of the devices, we want to guarantee that this aggregated output also provides guarantees against for the individual privacy of the devices that are participating. And in particular, the way we try to achieve this is to be able to guarantee that this aggregated output also provides differential privacy properties for the individual contributions. So existing works on secure aggregation usually addresses kind of a different subsets of these properties, where the cryptographic constructions really mostly focus on how we obtain this aggregated output, and then the differential privacy is more or less we're trying to obtain it as a black box use of the secure aggregation. But in one of the applications that I'll talk about later, which is kind of sparse histograms, it becomes challenging to be able to obtain these differential privacy guarantees just as a black box use of the aggregation protocols. So this would be some of the challenges that we'll be talking about later. So I also wanted to tell you that there have been different models about this aggregation, the secure aggregation, in terms of what architecture we are assuming for the server side. So I will also want to tell you a couple of words about the different things that exist and the fact that different architecture have been used in different applications. And I think they all come with their trade-offs. It's not necessarily obvious that one of them is the best one for every possible application. So the first one is kind of maybe the classical setting for secure aggregation, which really reflects what we have in reality, that in most cases we have a single server, and then we have these many clients. And we want kind of an interactive protocol between these devices and the server that gives us the aggregated output. And the restriction here is really that the only communication channels that exist between these devices have to go through the server. The devices don't know about each other, and they can only talk to the server. So any communication that should go between the devices has to be facilitated by the server. So in this setting, we have secure aggregation constructions that work both in the semi-honest and in the malicious models, where the caveat here is that when we talk about malicious security, we do have to assume the existence of PKI. Right? We don't know how to achieve malicious security without this assumption and without kind of knowing what the identities of the clients are and having some public keys about them, especially since all the communication has to go through the server. So when we see these malicious protocols for secure aggregation, they are kind of separated in two phases. One is setup, which includes this PK assumption to get some key between the clients. And then after that, we have the aggregation protocols that provide the fully malicious security. So when we talk about differential privacy in these protocols, this is the setting where most of the differential privacy results are in this black box access to the secure aggregation functionality, where we either talk about using the aggregation as a way to achieve differential privacy, and in particular, having kind of the noise that is inserted across all of the clients aggregate to the right amount of noise that we need for the final guarantee. Or if we go through this shuffling step, we have results that show you that you can implement a shuffling protocol just assuming a secure aggregation protocol. So there you can use this amplification by shuffling to achieve differential privacy, but both of these don't quite get you the central differential privacy guarantees that you want to, that would give you the optimal accuracy. And moreover, when we talk about these malicious adversaries, and when we assume that the server is controlling a fraction of the clients, now we have these trade-offs between the accuracy and the security that we want to be achieving, because we either want to have enough noise coming in the system so that you guarantee that even when you exclude the corrupt clients, you still have enough noise for the final output. Or if you want to optimize on the accuracy, then you might end up in a situation where if the corrupt clients reveal their noise to the server, you will not have the optimal accuracy. So these are kind of things that one needs to think about when you really want to get to the differential privacy guarantees. So I also wanted to mention that there have been solutions that solve the same question, but assuming that instead of one server, you have a second server, and you have, this helper server doesn't learn anything, doesn't learn any inputs, any outputs, but it's there in order to facilitate the computation. And one crucial thing that these protocols come up with is this non-collusion assumption, saying that like, you have two servers, but you will assume that they are not colluding. Of course, this assumption seems like something that weakens the model. The positives that come from these models is that these constructions usually are one-shot contributions from the clients, right? So clients participate only once and forget about it. So you don't have to deal with these issues of like clients dropping out and figuring out how to change your protocols. Most of the computation is kind of outsourced to these computationally powerful parties. And then in this setting, it's easier to achieve the central differential privacy if the servers are the ones that we rely on to add the differential privacy noise at the end. And this two-server model actually have been used in several applications, which include starting with Firefox, considering this for their telemetry collection. Then this model was the one that was used in the exposure notifications private analytics that were running alongside the exposure notifications app that Google and Apple had jointly developed. And more recently, there is a blog post that's coming from Apple, which is showing how this two-server model is used for learning iconic scenes in some of their photo apps. So I think this two-server model, which comes with this kind of maybe not optimal collusion assumption, is appropriate in settings where you already have multiple parties that have incentives to collaborate in this aggregation setting. And once you are in these multi-party settings, maybe you can assume that this two-server model is not so kind of unattainable in practice, right? And now that we started talking about multiple servers, I also wanted to tell you that there is a proposal actually for a system that's also in 3 parties. So there is this group which is called PATCG, which stands for Private Advertising Community Working Group. This is a working group in the W3C, and this working group is looking at the questions of how do you design a privacy-preserving APIs that will kind of help the web ecosystem when third-party cookies are deprecated from all browsers. And in this working group, there is a proposal which was written jointly by Mozilla and Meta that essentially is designing an attribution API that is an MPC system which relies on 3 parties. What they need in this attribution system is more than aggregation, right? Like aggregation is kind of the final phase, but before aggregation, you need to do some more complicated logic, which is attribution, which kind of matches impressions and conversions. And once you start needing anything more than aggregation, right, obviously, if you're in this like few parties MPC model, things are easier to achieve. So the reason that they chose these 3 parties is because of efficiency consideration, because of the scale of what they want to do, and because of the efficiency they need. So, of course, you trade off this with the non-collusion assumptions between these parties, but I just wanted to give you some examples where people are already considering moving to this more server model. All right, so now that I just put forward what are these different models and how they exist in actual applications and deployment, let's go back to our single server model and see what kind of results we've had on this recently. So I will start by overview with the kind of the template that essentially all secure aggregation, all single server secure aggregation start from, and then they kind of differ at how they modify it. So the basic idea that was introduced in the first paper that defined the notion of secure aggregation for federated learning in 2017 is that devices are going to share these pairwise masks. So every pair of devices will have to shared mask. And then when these devices are sending their inputs, they are going to use these masks, pairwise masks, to hide their input. And in particular, for each pairwise mask, one of the devices that has the mask will add the mask to its input, and the other device is going to subtract it. So it's easy to see that once you add up all of the contributions from all devices, you get exactly the sum of the inputs, and you cannot learn anything else. And I want to emphasize here that what these protocols do is that they share a short seed, and this short seed is expanded using a PRG to match the length of the input, because in practice, these inputs are quite long, especially when you talk about the gradient updates in the context of federated learning. So this will be an important point in one of our kind of optimizations that is going after more computational efficient solution. So this protocol is nice, but of course it has to reach or meet the challenge of what happens, because it's already an interactive protocol, and you can have these dropouts that I mentioned to you initially. So what you need to do in order to kind of guarantee output even when some of the devices drop out. So here, if P4 drops out, you can see that some of the PRG masks remain, and you cannot recover the aggregate of the input. So the solution that was proposed is that what you will do is every party will share the seeds that these pairwise seeds that they have with other participants in the protocol. And if some of the devices happen not to contribute their masked input, the server will ask the other alive devices to kind of recover the seeds that were not contributed and that are still masking the input, and will be able to obtain the final output. Of course, this comes up with some attacks that if the server is misbehaving, it can ask for the masks of everybody. So the way that they fixed this issue is by adding another type of mask to the input, which is called the self-mask. And the bottom line is that every client will contribute or will send to the server either this pairwise mask for a device or the self-mask. And I'm not going to go in detail, but it's easy to verify that with this construction, you kind of handle the issue of a malicious server that might incorrectly report that devices have dropped out. Because what happens at the end is that if a device drops out, then its shared mask is not contributed, so you need to reconstruct only the pairwise seeds. And if devices has sent the masked input, then its neighbors will contribute these self-masks. All right, so now what I was going to tell you is about these challenges about the computational bottlenecks, which I think became obvious only when this was deployed and actually started running in the context of federated learning at Google. And what happened is that suddenly these PRG evaluations that seemed kind of very fast at first and innocuous turned out to be a main computational bottleneck, because these inputs in reality are very, very long, and you have to expand a lot of seeds. Like the first protocol that was implemented had pairwise masks between every 2 clients. So you had a full, complete graph that defined a neighborhood relationship that determined what masks are shared between clients. So the complexity of how many masks and how many expansions you have to do was actually the number of clients times the input vector length. So that's how many expansions the computation for the expansions had to be. In a follow-up work, we improved this number of how many neighbors you have and you want to share masks with to be only logarithmic in the total number of participants. So this computation was reduced. Right now, you had only log number of clients, but still was a very kind of significant bottleneck, especially if you want to run secure aggregation across many clients. And a major kind of cost here was the fact that you had to first expand the seed and then use this expanded seed to mask your input. And the question was like, can we somehow do this combination of the seeds before you do the expansion? So really the expansion, running the PRG expansion was a main bottleneck. And it would have been nice if we can first combine these short seeds of the masks and then do the expansion. Obviously, this with the initial construction of PRG expansion was not going to work. There was no way to first combine the seeds and then apply the PRG. But the way we managed to solve this is to actually go to lattice constructions, which was kind of surprising that you will go for efficiency instead of using AES to using RLWE. But what this construction allowed us to do is really to achieve this combining of the masks before you do the expansion. And in particular, now the way we were going to mask the input was to essentially do RLWE encryption, where what happens here is that the secret key, you can have the secret key to be short, and then the way you will be encrypting, you're essentially first stretching the key into this larger space that matches the length of your input, and then you can kind of mask your input by doing RLWE encryption. So the important property that the RLWE encryption here needed to satisfy was that this is both key and message homomorphic, which means that when we are adding these encrypted inputs, you are both adding the messages, but also adding the keys. And this adding of the keys was important because, as you remember from the previous slides, you had to have this cancellation of masks in order to be able to obtain the final output. So I'm telling you here that this is RLWE encryption, but this is not really an encryption because we will not have a decryption step. But rather what will happen is that the way all masks will be combined at the end will be such that all the self masks, so right now all the masked inputs are encryptions under these combined secret keys of the corresponding inputs. And the property that we are after is that once we have added all the masked inputs, we will know exactly what will be the key under which the final aggregate will be encrypted, which will be all the self masks, and we'll be able to provide that key to the server, and this will enable it to obtain the final aggregate. So the way I'm describing this, I keep on calling this encryption, but this is not quite an encryption, and this cannot be proven secure directly from RLWE. And in particular, the reason for this is that what happens here is that we are releasing many RLWE samples but they're under correlated secret keys, right? You can think of these samples as the first n-1 of them. They have independently sampled secret keys, but the very last one of them has to have a secret key, which is kind of the sum of all the first n-1 keys. So now you need to prove security that this scheme is still secure under RLWE with these correlated keys. And this doesn't follow directly. So one idea was like, oh, can we add kind of more noise to this encryption so that we can hide this correlation between the secret keys? And of course, the question is how much noise so that you can still have optimal parameters and also the computation that we are after, right? We are after here improving computation that comes from expanding a PRG. So the kind of the first idea that we had was adding uniform noise here, and a lot of uniform noise that pushed quite a bit the parameters for the RLWE. But finally, our result, what we managed to achieve in our result is to show that it's enough to add noise that's only coming from the same distribution as the regular RLWE noise. So we managed to achieve security with adding not too much noise, maybe twice as much noise as the original construction. And kind of the proof of security that we have goes through this hint RLWE, which is an assumption that tells you that in addition to the usual RLWE sample, you also have a hint, which hint is kind of the noise that was used in the sample, but also this noise is hidden with another type of noise that is sampled from a different distribution. And there is a reduction between RLWE and hint RLWE where, of course, you incur some loss in the variance for the parameters. So if E and F were coming from this Gaussian distribution with variance sigma 1 and sigma 2, then the variance of the resulting RLWE for which you get the reduction has this form, right? It has this increased variance. So our final proof goes through this hint RLWE and eventually to RLWE. So now let's see what we achieved with this construction, which kind of we call optimal secure aggregation construction. And in particular, let's look at this in the context of the existing work, right? This first column is just computation in the clear, just to kind of understand what is the overhead we're incurring with the secure construction. And then the second column is this work that we have, which really goes to the sublinear communication and computation complexity that uses only log n neighbors. And the main kind of improvement that happens with this RLWE construction is that in the client computation, you no longer have this cost, which is the length of the message times the number of neighbors that you have, which is log n. In particular in this Bell et al. Construction, but it's in the construction with the RLWE, this becomes a plus, which is a significant saving. So this is the client computation. The server does computation, which is proportional to the number of clients times the computation that each client does. So this reduction from multiplication to plus was a significant kind of improvement. One thing that was expected to happen is that going to this RLWE construction, we will save on computation, but we will increase our communication. By the way, the inputs are encoded using this kind of RLWE type of encryption thing versus the PRG one-time pad. In reality, for the concrete benchmarks with some numbers, so this is the number of clients, so up to 1,000 clients, and these two rates are the number of dropouts and the number of malicious clients. The concrete numbers didn't look that much worse than the PRG construction. So we gained a lot in terms of the computation, and we sacrificed very little communication. So if we looked at the benchmarks of actual implementations, what happens is that for the clients, once the inputs become sufficiently long, right, this construction is specifically tailored for the setting when the inputs are long and you have to expand a lot of the PRG. So for the client's computation, we were saving about 8x when the inputs become longer than 2 to the 13. And then for the server computation, this was much more significant because the server computation, right, was proportional to the number of clients. So for the server computation, we saw from 8 to 100x improvement as you went to longer and longer inputs. And again, like the more dropouts you have, the higher rate of dropouts you tolerate, these kind of savings become more pronounced. All right, so this was kind of what was the first result, is that essentially what we are telling you is that you shouldn't use the PRG construction. You should use RLW to mask your input, and this is optimal for your computation, and you get almost no penalty in the communication. So now let me move to input validation. So what is input validation? This goes back to this question of like, what are we trying to protect against malicious clients? Here, what we're trying to protect against malicious clients is these clients trying to make the output models unusable, right? And they're like targeted and untargeted attacks, where the untargeted are kind of the easier. They just want to make the final output unusable. The targeted attacks are much smarter. They are trying to change the behavior of the model on particular inputs. And there have been examples of both of them. There was also a couple of works that were essentially showed that one way to significantly thwart this type of attacks is to be able to bound the input norm of the vectors that each client is providing. So the kind of solution that we try to develop is, can we have every client provide a zero knowledge proof that will guarantee that the norm of its input vector is bounded? And of course, the main tricky question here was how to do this efficiently, right? Trying to apply a generic zero knowledge proof was not going to get you anything efficient. And in particular, since as you will see in some of the following slides, this is not just a zero knowledge proof of my inputs. Some of my inputs, in particular these masks, are correlated inputs with the other clients. So now you want all of the clients to be able to jointly compute this kind of zero knowledge proof, which shows that they have consistently chosen their masks that are used for the encoding of their inputs. And then on top of this, that their inputs satisfy this input vector norm bounding. And if you want to do input validation, there are two types of flavors of functionality that you might want to achieve. The easier one is detect only, which means that the server can detect if there was misbehavior on some of the clients, but then the protocol aborts. So that's easier to achieve. And then there is the robust protocol, which has guaranteed output and this means that the server is able to detect the misbehaving clients and then is able to exclude their inputs from the final aggregation. So before we started our work, there had been already papers that were looking at the same question. So this Roffel paper and this Eiffel paper. So what happened in their construction was that the client communication incurred this additional overhead, which was proportional to the number of clients. So Roffel and Eiffel have, right, you see that here with Eiffel, this is multiplicative overhead with n square, and here this is additive overhead of n, which is the client communication. But then when you look at the cloud computation, both of them incurred overhead that's linear in the number of clients. So what we brought with our construction was to make the overhead only polylogarithmic in the number of clients, which, as far as we know, is kind of also the optimal way to achieve these properties. And to get the robustness, so in our paper robustness, we have it technically written only in the semi-honest setting. So this means fully malicious, this means semi-honest. We think this is generalizable to the malicious, but we never got to write it down. But this is kind of the improvement that we achieved over these papers. And when you look at the actual numbers, really this is very significant improvement in terms of the communication and the computation that each client and especially the server also needs to do. Okay, so what is the idea of our approach? I mean, this is kind of the template idea that I was mentioning you, is that every client will be committing to their input vectors and then will be committing also to its masks. And note that here if we are working with the PRG construction, this construction works with both the PRG secure aggregation and the RLW secure aggregation. But if you are talking about the PRG construction, you need to commit to the already expanded seeds. You cannot do the PRG computation inside of the zero knowledge. And what we will do is that each client will provide two types of proofs. One will be the input vector bounded norm, and the other one will be the correctness of the input encoding, which means that your input was really masked with the committed masks. And then all clients together will have to give or generate distributed proof that shows that they used consistently their masks. And it turns out that if you only need detection, it suffices to prove that the masks across all clients sum up to 0, even if they didn't choose them exactly correctly as they were supposed to do. As long as all of them sum up to 0, I think this is sufficient for the final guarantee. If you want to go after robustness, you really need to try to prove consistency of these pairwise masks that the pairs of clients are contributing, and this becomes more complicated, more rounds of interactions for this proof. So let me just give you kind of an idea of how these proofs work. So the first one is the one where the clients want to prove together that their inputs, their masks were consistent. And here I'll be talking only about the detection protocol. So they want to prove that their masks sum up to 0. So for this, what we did is we took the Schnorr protocol, which could easily allow us to prove this statement if all the inputs belong to the same party. And then we noticed that you can distribute the Schnorr execution, since this the way you compute the final message that depends on the challenge is linear in kind of the linear in the secret witness that you have, and also linear in the randomness that was chosen in the first message. So you can have the clients compute the answer to the challenge in a distributed way. In order to protect against malicious server, the trick thing is that you need to provide also the zero knowledge. And in these protocols, the zero knowledge comes only when we have the non-interactive version. In order to get to the non-interactive version, you need to assume that all the clients have the same view, but this is not the case, right? The clients don't have the same view. They see different messages. So we had to go around this with a technique that has the server commit to its challenge before any inputs are sent, and use some kind of equivocal commitment for that. So then let me tell you how this was the part that shows that all the masks were chosen consistently. Now you had to do the proof that shows that the bound of your vector is really bounded. The norm of your vector is really bounded. So what happens here is that we have a vector that has n components, and you want to show, so here this is an example for the L infinity norm. We have a way to generalize this to L2, L1, whatever norm you want. So what we will do here is we want to show that each of the inputs is within some range. So this is equivalent to showing that this relation is greater than 0. And then for this one can use the Lagrange four-square theorem, which says that it suffices to find 4 integers such that their squares sum up to this value. And this was a technique that had already been used in this paper. I don't have the citation here of the paper, but the paper is Gentry, Halevi, Lubashevsky. What we did is we noticed that we can optimize this after we for the setting where we have integers, all our values are integers. So this value becomes bigger than 0. And essentially what this says is that it's sufficient to find 3 integers such that their squares sum up to this updated value. So essentially what you need to do to prove this norm bounding is to prove that you know 3 integers such that their squares equal to this relation, this expression in terms of your 2 bounds, public bounds, and your secret value. So one tricky thing was that this theorem holds over the integers. And then when we are using proof systems, these proof systems work mod Q. So additional thing that we needed to prove is that there is no wraparound mod Q. So we essentially needed to prove that kind of the bound, the L infinity bound of these values, the values that come from the Lagrange theorem and the expression in terms of our input doesn't wrap around Q. So, okay, so now what did we do? We had to prove an L infinity bound on a vector, and we reduced it to an L infinity bound on another vector. So this seems like kind of, initially it looks useless because we are reducing the same L infinity to another L infinity. But the key point here is that this second L infinity bound is very loose. The actual values here are expected to be much, much shorter than Q. So what we can leverage was this Johnson-Lindenstrass theorem that tells you how you can compress essentially this type of statements. And in particular, it tells you that, and this is a statement from the same paper, Gentry, Halev, and Lubashevsky, which tells you that if you want to prove some L infinity bound on a vector, let's say T, but in reality, you will be giving a proof, a much looser proof, which is kind of this gamma times T, and there are specific bounds on what gamma should be. So if you want to just prove the much looser bound, you can reduce this L infinity proof into a vector inner product proof. So there are ways to find Y and T vectors such that the only thing that you need to prove is the inner product between your input Z appended with this Y and the vector T, where the length of these 2 vectors is the length of the original input plus some security parameter. So this is a very useful theorem that essentially allows you to compress a lot the dimension for the vectors on which you are trying to use inner product. And what you end up doing is reducing this range proof to an inner product proof. And in particular for our implementation, we used bullet proofs to implement these inner product proofs. We also had some other optimizational tricks. A lot of these tricks, again, we borrowed from the Shai's bag of tricks from that paper that I mentioned already twice. But essentially what happens is that you have a bunch of inner product proofs. So you can use short ZIPL to reduce the dimension even more. And then there is a way to avoid having to commit twice to these values X prime or U or V or W. Because if you commit twice to them, you have to prove consistency, et cetera, et cetera. So there are ways to optimize and reduce the concrete length of the proofs. So we implemented this, and we implemented this both with the PRG construction for secure aggregation and RLWE. So with the PRG construction, what you see is that the computation time on the client for small inputs is even under a second, up to 2 to the 13, and then it runs in tens of seconds, up to 2 to the 20. Communication also seemed to be reasonable, starting with a couple of kilobytes and going to 2 megabytes for 2 to the 20. I think what you would expect is that when you have larger dropout rates, you see more significantly increase in the computation cost for key recovery, which is basically how you handle the dropouts. And this is this property of the PRG, which is kind of bad, that it scales with the length of the input. So the longer your input, the more significantly this cost for key recovery increase. And I guess with the RLWE construction, The time and the communication on the client was slightly worse. But what you gain is that your recovery cost stays relatively the same, even as the input length increases. And the bottom line is that for many of the parameters, actually, the RLW construction is still better. Note that here we are using RLW construction with the proofs which are bulletproofs. So it's an interesting open question if you can change the actually the proofs to be using also RLW techniques. We haven't done this so far. Okay, so I'm a little lost about how much time I have left. I think we started much later, so I think I have some. Oh, I have 2 minutes. Okay. So I'll take a little more than 2 minutes, but not too many. I just wanted to tell you what's hard, what we don't know how to do with the single server, and what we ended up doing actually with 2 servers, because even with 2 servers, it was kind of hard. So this is the question of sparse histograms. What does this is a sparse histogram? Is like the histogram domain is much larger than the number of clients you have. So what happens is that you have this very sparse histogram that you have. It's mostly zeros. There are a few buckets that are non-zero. And what you want to do is you want communication and computation that is proportional only to the number of clients, that's independent of the domain size. And here we are really interested in the differentially private output. So I want the error that you get for these buckets to be independent of the domain size. So the combination of these things together makes it tricky. Using directly secure aggregation in this black box way, there is no way, like the communication explodes with the domain size. Trying to go through these shuffling techniques that use secure aggregation, again, you don't get the optimal DP parameters that you want, and the communication is quadratic in the number of clients, not linear. There are a bunch of heavy hitter type of solutions that come from the DP community, which rely on these counting oracles, but those don't get you the independence on the error of D. These things are proportional to the depend on D in terms of error. So what we want to essentially implement is in some way the optimal solutions for this problem in the central model for DP. And the kind of way that these constructions work in the central model is that you compute the histogram, then for all non-zero entries, you add noise and you threshold. So this is how you get these optimal errors. And the question is, can you implement this type of functionality in secure aggregation setting? Now you have to do this threshold, which is it's not clear how you do them. So even when you go to 2 parties, right, the way, if you want to use like generic 2-party protocols, one way is to take and sort all your data and then add noise and threshold. So these constructions don't meet the efficiency goals, both in terms of asymptotics and concretely are very far out. So what we ended up doing is allow some additional differentially private leakage between these 2 servers. And we obtained a solution that kind of goes through these conceptual steps. We found a way to take the encrypted records where we encrypted the index for the aggregation using a homomorphic type of encryption, and then the value are also homomorphically encrypted. So we found a way to insert dummies, which was kind of the most interesting part of the protocol. When we have these large input domains and then transform these histograms into anonymous histogram where the indices are not already present. And we found a way to apply this thresholding mechanism in the context of these anonymous histograms, where again, our guarantees for the 2-party computation are more of these differential privacy flavor guarantees. And then after we apply the thresholding in these anonymous histograms, we map back to the differentially private histograms where we reveal the indices. And as I mentioned, kind of the most interesting thing is how we insert these dummy items. And for this insertion of dummy items, our techniques rely on two properties. One of them is that you can do duplications. Even when you don't know what index your contributions are for a particular bucket, you can generate new dummy records using the same encrypted index. So this way you are achieving the differential privacy for the buckets that have a lot of items, that have a lot of contributions. And for all buckets that are below a certain threshold, we can achieve the differential privacy guarantees by just generating dummy records for each of those possible values from 0 to t. So, and then again, as I mentioned, these thresholding mechanisms, we leverage more aggressively the differential privacy weaker model for the two-party computation. So again, we kind of benchmark these, and these protocols may be the most interesting is, I mean, they're much, much faster than any of these like two-party sorting and then adding noise. These protocols, their efficiency depends on the epsilon because, right, they work in this model where you are adding dummy items, and how many dummy items you're adding depends on the particular epsilon. So your efficiency kind of is proportional to how much you pay with efficiency for the privacy you want to provide of the output in some way. Okay, so just a call out for all the techniques I didn't mention, right? There is this whole line of works that is trying to do secure aggregation that relies on this idea that you will, instead of having all of the clients communicate with the servers, you select subcommittees that kind of do most of the work on behalf of the clients. I think we still don't know how to do this sparse histogram in these models. I'll be happy if somebody proves me wrong. One thing to be careful with these protocols is that you still don't want, even the parties in the committee, you don't want them to do work proportional to the number of clients. This could be an issue. Interactivity for sure has a very, very high price. Yeah, you still want to support dropouts, etc. Okay, I think I'm a little over my 2 minutes, but with this I will finish, and thank you for your attention. I assume I ate my time for questions, but
no, but we can get 1 or 2 questions while Nati is coming on stage for the next talk. So if you have questions, please come on the microphones and ask the questions. I have one until we see if somebody else has a question. So the robust version where you want to guarantee output delivery, how efficient or not it is, because I saw you didn't have graphs, and how many rounds is it? I guess it depends on the number of dropouts there. So is it efficient?
So the number of rounds, I think, scaled log with the number of dropouts plus malicious parties. The asymptotic thing, so the overhead before depended on log n, now for the robust depends on log square n. Oh, again, this we have it written out only for the semi-honest. With the malicious, some of these constants might change. We don't think asymptotics will change.
I see. Maybe has a question.
Just a quick things about kind of practice versus theory. So for this, range proofs, I know they come up not just for aggregation, but like for blockchain, like to prove balance. I saw that the whole point of like bulletproof, the main application was just straight up to do those range proofs. You're saying that's not the most efficient techniques, you just combine it with something else?
So we tried to do directly the range proofs with bulletproofs, but the dimension on which you need to do them are enormous. So what we did is first to reduce the dimension using this Johnson-Linden-Strauss. So now you do use bulletproofs, but the actual range on which the vector sizes are much, much smaller. So now for this, you can kind of run them.
Or even for one number, you're saying when you do bit decomposition? I mean, even for one number, the dimension is, right? If I just want to do a range proof that one number is not negative or something.
I mean, if it's for one number, it would be a difference in constants. Right. But here we are talking about vectors. So, right, 2 to the 10 to the 20 vectors. So in that setting, then it matters.
Also, you're saying still bulletproof is like the best, but combined with like sparse, whatever, dimensionality reduction, you...
Yeah, you like this reduction in the dimensions, it actually matters quite a lot.
Cool.
Okay, I think think.
Yeah, thank you, Mariana. We have no more time for questions. Please, thanks again, Mariana. So next we have two contributed talks. Can you test the microphone? Everything works?
Can you hear me? Great.
And your clicker works? Everything is fine?
Check it.
Okay, great. So next we have Nati Peter, and he's gonna talk to us about smooth lower bounds for differentially private algorithms, their padding and permuting fingerprinting codes. Thanks.
Thank you, Antigone, for the introduction. So my name is Nati, and I'm going to talk about our new paper, the smooth lower bounds for differentially private algorithms via padding and permuting fingerprinting codes, which is a joint work with Eliad Sfadia and Jonathan Ullman. Differential privacy presented by Dwork, McSherry, Nissim, and Smith is a privacy setting or framework that enable us to ensure the privacy of individual inputs when applying algorithms over sensitive databases. In order to explain what is differential privacy, we consider neighboring databases, which are two databases that differ in exactly one input. Generally speaking, we say that an algorithm A is differentially private if for every two neighboring databases, D and D prime, the outputs of the algorithm A on the databases D and D prime is almost the same. So according to the definition of neighboring databases, we can say that the algorithm A, which is differentially private, should preserve the privacy of every individual input from the database. It is not necessary to get the formal definition of differential privacy for this talk, but I'm just going to tell you that differential privacy uses two privacy parameters, epsilon and delta, that determine how similar the outputs of the differentially private algorithm A over every two neighboring databases. One of the most fundamental problems of differential privacy is the averaging problem, in which we have n points of dimension D. All of them are contained inside a ball of diameter R, and we would like to estimate the average of the endpoints. An algorithm A is said to be averaging lambda estimation algorithm if with high probability we have that the distance between the output of the algorithm A on the endpoints and the real average of the points is at most lambda R, where the distance is measured using the Euclidean norm. In other words, we can say that the algorithm A is actually a lambda estimator for the average of the endpoints. In the differentially private variant of the averaging problem, we also require that for every two neighboring set of points that differ in exactly 1 point, denoted by x and x prime, the outputs of the lambda estimator A on the sets of points x and x prime is epsilon delta similar, according to the definition of epsilon delta differential privacy. we now start by considering the case that the location of the ball containing the points, where we assume that the points are all contained in some ball of diameter r, is known. And for simplicity, we can assume that the center of the ball is the origin. So for that case, when we look at the parameter lambda, which is smaller than 1, we have an upper bound on the number of points n required for ensuring differential privacy, which is shown by Dwork et al. And Ban and Steinke, while Ban et al. Proved a matching lower bound. On the other case, when lambda is greater than 1, we can simply return the center of the ball, which by our assumption is the origin. And in that case, even for 1 point, we have a lambda estimation of the average, which is also differentially private. Now we consider the case that the location of the ball containing the endpoint is not known. And for that case, for every possible value of lambda, we have the same upper bound as in the previous case, showed by Caro and Vadhan, Sfadia et al., and Ashtiani and Liao. For lambda smaller than 1, we have the same lower bound of Ban et al. However, for lambda greater than 1, we don't have any non-trivial lower bound. And this is one of the problems that motivated our work. Since our results uses fingerprinting codes, I will tell you about the history timeline from fingerprinting codes to differential privacy. So fingerprinting codes were introduced by Bonnet and Chow, and unfortunately, I don't have time to tell you what are exactly fingerprinting codes, but I just tell you that fingerprinting codes contain n code words of length d that are used to detect unauthorized copies of digital data. So later, Tardos showed an optimal construction of fingerprinting codes in which the length of each code word D is theta of n squared. Then Ban et al. Showed how to use fingerprinting codes, and in particular, the fingerprinting code of Tardos, in order to show lower bounds for differentially private algorithms. After that, Dwork et al. And Ban et al. Present the notion of fingerprinting lemma, which is a more clean and elegant tool that used to achieve lower bounds for differentially private algorithms by using fingerprinting codes. Now I will tell you a little bit about our main technique, which is a new padding and permuting algorithm used to obtain hard instances that will be used to achieve our lower bounds for the case that lambda greater than 1. So here I will tell you about our technique for the averaging problem, but our technique is more general and can be applied for fingerprinting codes. So let's start by looking at n hard points of dimension d used to obtain the lower bound of Ban et al. For the case that lambda is smaller than 1. As before, we can assume for simplicity that all balls are located inside a ball in which the center is the origin, and the diameter of the ball r is square root of d, as shown in the work of Ban et al. We also consider an higher dimension d prime, which is theta of lambda d, and the diameter r prime, which is square root of d. So in order to obtain hard instances, for the case that lambda is greater than 1, we take the n hard points from the lower bound of Ban et al., and we pad each point and get eventually n points of dimension d prime, which is higher than d. And then we permute the coordinates of each of the padded points according to the same random permutation. In this way, we eventually get n relatively concentrated point of dimension d prime, and their location inside a larger ball of diameter r prime is not known. So in other words, we eventually keep the hardness of the original n points, which eventually lead us to our desired lower bound for the case that lambda greater than 1. Now I will tell you about the applications from our padding and permuting technique. So as I just told you, our first application is a lower bound for averaging estimation differentially private algorithms. Our second application is lower bounds for clustering approximation differentially private algorithms. And our third application is a lower bound for top singular vector estimation differentially private algorithms. As you can see in this slide, the privacy parameter epsilon and delta for all of our lower bounds are 1 and 1/4n respectively, which are considered to be bad privacy parameters. However, this only makes our lower bound stronger. Just to mention, a good privacy parameter epsilon is considered to be a small positive constant, and a good delta is considered to be a negligible function of n. So to conclude this talk, in this work, we showed lower bounds for differentially private algorithms for several problems, where differential privacy, as I mentioned, is a notion used to ensure privacy of individual input. As in previous work, we used fingerprinting codes to obtain our lower bounds, but in our work, we develop a new padding and permuting technique that enable us to get the new lower bounds. One more thing that we showed is a new fingerprinting lemma, which is a much more cleaner and intelligible way to obtain lower bounds for differentially private algorithms. Our new fingerprinting lemma requires much weaker assumptions compared to previous fingerprinting lemmas, which may be of independent interest for future work. That's it. Thank you.
Thank you. So while the next speaker is setting up, we can get some questions. Again, you can come at the front, the mics. While we're waiting, I want to ask about the model. So when you do the padding and permuting, so what is the model? Like, who knows the permutation? You do like CQ permutation. So I assume the inputs are, the inputs X come from different users, right? So can you explain your model?
Yeah, the user come from different models, but the permutation must be completely secure. It's a random permutation, and it's the basic differentially private setting.
Okay, so you assume some secure permutation.
Yes, exactly.
Great, thank you so much. Let's thank Nati again. Can you check the clicker? Okay, great. So next, we're gonna have Yang Zibo. I hope that's the right.
Yeah, it's correct.
Yang Zibo Wang. She's gonna tell us about sparsity preserving differentially private training of large embedding models. Thank you.
Okay, thanks for the introduction. So hi everyone, I'm Yang Sibo from Princeton, and today it's my great pleasure to share our recent work, sparsity preserving differentially private training of large embedding models. This is a joint work with my amazing collaborators at Google Research, including Buddy, Pratish, Ravi, Pasan, Amr, and Shula. Okay, so let's get started. Let's start with the background first. So nowadays, machine learning applications involve the usage of massive non-numerical data, such as the user data and product data in the recommendation systems and text data in NLP applications. However, machine learning algorithms typically take numerical data as input. So how can this non-numerical data enter the machine learning pipelines? The solution is a model we're going to explore today, the embedding models, which map categorical or string-valued inputs into fixed-length embeddings, which enables integration of non-numerical data into deep learning models. For instance, to process a sentence, say, I saw a cat, for an NLP task, the embedding model will firstly convert each word into an index into the word vocabulary, and then fetch the corresponding word embedding. And these embeddings are then utilized as representation for the sentence. Typically, the word embeddings are also trained during the pre-training of language model for better performance. The vocabulary size of embedding model vary across different tasks. Typically for NLP models, it's usually tens of thousands, where for recommendation tasks, the vocabulary size can be much larger, reach several millions. However, these models also raise privacy concerns due to the collection of sensitive information like the individual demographic data, private chats, and medical histories. Therefore, there's an urgent need for preserving the privacy during the training of these models. Various techniques have been proposed to enable private data analysis, and among those, differential privacy, or DP in short, is a widely adopted notion that could formally bound the privacy leakage of an individual while still allowing for the population-level patterns analysis. And formally, a randomized algorithm is epsilon delta DP if for every pair of neighboring data sets that differ by at most one record, the distribution of the model on the two data sets only differ by a very small amounts defined by epsilon with failure probability delta. And in other words, DP makes it very hard for an attacker to tell whether an individual data point has been included in the training of the model or not. And for training the deep neural network with DP guarantee, the most widely used recipe is differentially private SGD. So given a batch of the gradients at each training step, the DP SGD will firstly clip the pre-example gradient contribution, and then average the clipped gradients, and finally add calibrated Gaussian noise to the average gradients updates to construct the DP gradients. The DP gradient is then used to update the model. However, directly applying DP-SGD to the large embedding models actually present technical challenges due to the sparse nature of the embedding gradients. Because these embedding models usually have very large vocabulary, and therefore the gradient updates are usually extremely sparse because each mini batch of the example only activates a very tiny fraction of the vocabulary entries. For example, as shown here, each example in the batch may have different activation pattern, which results in a very sparse gradients. And more important, this sparsity is very important for the efficiency of the model because it can be leveraged by customized APIs to provide efficient training. So if this sparsity is destroyed, then the training will compromise. However, when we are directly applying DP-SGD to the training of large embedding models, we're adding column-wise or the entry-wise dense Gaussian noise, which results in a dense DP gradient vector. And therefore, the training efficiency will be directly compromised here. So in this talk, we'll try to share some of our recent effort on how to effectively customize the general purpose DP-SGD for the training of the large embedding models. Specifically, we propose two sparsity preserving DP training algorithms for the training, from which we're able to achieve more than 10 to the 6 reduction in the gradient size, which translates into over 20 times word clock time improvement. Let's begin with the first proposal, which is a very intuitive one. We refer to it as DP Fast, filtering enabled sparse training, where we just pre-select the top K most informative buckets beforehand training, And then we'll only add Gaussian noise to these gradients, to the gradients of these selected buckets during the training. This is actually equivalent to training a smaller embedding model using a subset of the vocabulary. And K here is enough for us to control sparsity. However, this method is not able to adapt to varying activation patterns across different training batches. This issue becomes particularly problematic if we are dealing with online tasks, where the data distribution change over time. To address this issue, we further propose DP-AdaFast, an adaptive method for selecting the most informative buckets during the training. On a high level, for each bucket, we'll try to generate some DP contribution score based on the bucket-wise and example-wise counting, and then we'll only keep the buckets whose contribution score is higher than a certain threshold and add Gaussian noise to these gradients for updates. Specifically, for each mini batch, we will firstly compute the per example gradient and a gradient contribution map, which is a binary vector indicating which category feature have been activated for each example during the mini batch. And then we will aggregate all of the contributions with per example clipping applied across a mini batch in order to construct the batch-wise gradient contribution. We then add Gaussian noise with scale sigma 1 to the resulting contribution vector to ensure DP. And then the noisy batch-wise gradient contribution will be thresholded using a parameter tau to exclude the non-significant gradient entries to which only a very few examples in the batch contribute to. And finally, the algorithm updates the model parameter by adding the gradient noise with scale sigma 2 to the surviving gradient entries, which are highlighted in purple here. By dynamically adapting the feature selection based on the bucket-wise contribution, we're able to achieve an adaptive feature selection and also maintain the desired DP guarantee at the same time. The privacy accounting of DP-AdaFast is actually quite straightforward and can be done in a similar way to that of DP-SGD. We observed that the privacy cost of a single iteration here is actually equivalent to the composition of the two Gaussian mechanisms with scale sigma 1 and sigma 2. So overall, the privacy cost of the entire algorithm is no more than this shown sigma. Therefore, we could just solve the sigma from the standard accounting of DP-SGD and then obtain the sigma 1 and sigma 2 respectively and plug into our pipeline. Now for our evaluation. We evaluate the performance of our methods and compare them against vanilla DP-SGD and the previous proposal on both recommendation task and language understanding task. We're especially interested in understanding how do our proposal compare to DP-SGD and the previous proposal in terms of the utility and efficiency trade-off, and can we combine them to achieve even better trade-off, and how to properly set hyperparameters for our approach. Let's start with the utility and efficiency trade-off. Here, each figure has gradient size as the x-axis and model utility as the y-axis. In real-world applications, the decision to prioritize utility or gradient sparsity, which is a key factor for efficiency of large embedding models, usually depends on the task and available computation resources. However, it can be very hard for DP to control the sparsity because it doesn't provide a mechanism to tune the sparsity. But in all the evaluated methods shown here, DP-AdaFast, DP-Fast, and also the previous approach, they actually provide a way to tune the sparsity. But our approach, the DP-Fast and AdaFast, outperforms the previous work, DP-SGD, with exponential selection in terms of the utility and sparsity trade-off. We then try to translate these scatter plots into a gradient size reduction curve as shown here, while the x-axis is the utility loss or utility gain compared to the vanilla DP-SGD, and the y-axis is the gradient size reduction. The higher the curve, the better the performance. We find that the DP-Fast AdaFast actually gives us a better gradient size reduction compared to DP-Fast at the same level of utility loss due to its adaptive nature. And specifically on the critical Kaggle dataset, which is a recommendation task dataset, we're able to reduce the gradient size by more than 10 to the fifth, which translates into 20 times if we're using a specific API. And moreover, the best reduction for the language tasks, which are showing the right three figures, are much smaller when compared to the recommendation task. And this is probably because the vocabulary in the language task is already condensed, so there's very little room for us to improve further. But we then try to dive in more into the natural language task because nowadays, preserving privacy in those models appear to be very important because of their increased popularity. So first, we try to compare our proposal with applying LoRa, which is a way to allow for parameter-efficient fine-tuning via low-rank approximation on the word embedding layers. We observed that at the same utility loss, our method can achieve a higher gradient size reduction than LoRa. Additionally, our algorithm could benefit from the efficient embedding lookup via the customized APIs, where LoRa would still require the relatively expensive calculation via the matrix multiplication. And also, LoRa needs to adapt a pre-trained model where our algorithm can work in both pre-training and fine-tuning stage. We also compare the gradient size reduction we achieved on Robota model, which was the backbone model we were testing on, and another model, which is XLMR, a multilingual model with a much larger vocabulary. We do observe that DP-ADFS results in a larger gradient size reduction for models with larger vocabulary, and this is potentially due to a larger room for specification. We finally explore the potential of integrating DP-Fast, which involves a global selection, and DP-ADFS, which involves a batch-wise level selection to enhance the performance. Specifically, we firstly pre-select a subset of buckets and then subsequently train on them using DP-ADFS, and we call this DP-ADFS plus. We find that using the combined algorithm, we're able to further push the best gradient size reduction from 10 to the 5th to 10 to the 6th times. And this can be attributed to the complementary strengths of the two algorithms. And another thing we evaluate on is on the online recommendation tests, because they are usually more challenging due to the non-stationarity pattern of the data. We observe a consistent improvement of the combined approach over individual algorithms, which aligns with our previous observation. There are also some suggestions on how to set the hyperparameters, including the sigma 1 and sigma 2, and also the thresholding pattern tau, but I'm not going to show more details here. If you guys are interested, you can just refer to our paper. And finally, to summarize, in this work, we effectively address the disjoint gradient sparsity pattern challenge when applying the general purpose DPSGD to large embedding models via the proposal of DP-Fast and DP-ADFS. We show that we're able to achieve a substantially sparser gradient with reduction in size of over 10 to the 6 times, which translates into 20 times word clock time improvement compared to the dense gradients produced by vanilla DPSGD, while still maintaining comparable level of accuracy. For future work, we're interested in exploring how to leverage the specialized hardware to further optimize the computation cost. And also, we are interested in the integration into non-centralized training paradigms, such as federated learning. With that, I want to conclude my talk, and thank you for your time, and I will open the table for the questions.
Thanks for the talk.
Oh.
I was wondering why do you have any intuition for why you see improvements over the exponential selection technique?
Why this is better than the exponential? Yeah. I think, personally, I do not have a very good answer for that. But one thing we observed in their paper is like their privacy analysis might not be tight for the exponential. Yeah. Well, in our case, we're using the sigma 1 and sigma nu composition, and that is a tight analysis.
So you're using Gaussian DP? Or?
Yes. Thank you.
Thanks for talk. So if I understand correctly, the first step is to select the buckets. Is this selection done privately or?
Yes, it's done privately.
But so you need to compose this private selection and the Gaussian mechanism.
Yes, so as shown in our, I'm not sure if this is easy to go back. So we have a privacy analysis here. It's way back. Yeah, here.
Sigma 1 and sigma 2 corresponds to the two Gaussian noise.
Yes, sigma 1 is added to the contribution, and sigma 2 is the final Gaussian noise added to the gradients.
So where is the, the epsilon for the private selection?
So in our evaluation, we mainly report with epsilon equal to 1.0 and 3.0 and 8.
That's me. So there are three mechanisms, private mechanisms. One is for selection and other two are for Gaussian noise. And in your private analysis, you need to compose these three mechanisms?
Oh,
in-
there are actually only two of them. One is for adding noise to the contribution, which is sigma 1 here. And the second one is sigma 2, which is for adding to the gradients. And this is in this proposal. And in the previous proposal, the DP Fast, we do a composition. So we do a pre-selection of the top K using DP selection. And then we just do DPSGD on that with another epsilon. And then we do composition of those two. So there's no string mechanism. In each method we're having here, there are only two mechanisms.
Okay, so
And we do
yeah,
composition.
so in DPLFS, it also enjoys like the sharp analysis of Brilliant differential privacy. Okay.
Yeah. Okay. Thanks for the question. Yeah. Thank you.
Yeah, we have no more time for questions. Let's thank again Jan Sibyl. So we'll be back at 10:45. We are running late 15 minutes, so we'll be back in 10:45, so we'll follow the schedule.